Hey guys, welcome back to General Chemistry. We're going to continue on here in chapter 9. So we're going to continue to look at energy and how it's associated or applied to this subject of chemistry. So first thing I need to introduce to you guys is the unit of energy. So the SI unit of energy is the joule. So this is the unit that we will use for the remainder of this chapter. So joule is the unit we use. Joules, these numbers tend to get very large very quickly. So if we're not using joule, another version of this that we will use is the kilojoule. So that's just adding that prefix, making that number a little bit more manageable. So joule or kilojoule will be where we live. Other units that we use for energy or that you've seen would be like a calorie. So calorie is the amount of energy needed to burn something. So calorie is also a unit for energy, and we typically see this in nutrition. But know that a nutritional calorie isn't just this teeny tiny regular calorie. A nutritional calorie is actually a kilocalorie. So again, these numbers get very large very quickly. So to reel them in, we use that prefix kilo, just like we would for the joule. But those are probably the two units of energy that are the most widespread. But again, we will live with joule. So anytime you see the unit joule, that will be your unit for energy. This chapter is called thermochemistry. Thermochemistry lives under a division of science called thermodynamics. So thermodynamics is defined as the study of energy and its interconversions. So first looking at this idea of energy, and then how does it change for us, like across the chemical reaction. So thermodynamics is kind of the broad, big umbrella that we're going to place all of this chapter under. There is a law that governs everything that happens in this chapter. So law is something that cannot be or has not been disproven. So this is the first law of thermodynamics, and it's the law of conservation of energy. So what this is saying is that during a chemical reaction, energy can neither be created nor destroyed. It simply changes form. So as we talk about energy being released or energy being absorbed during a chemical reaction, it's not that energy is just poof coming out of nowhere. It's actually being stolen or converted from something else. So just the first law of thermodynamics, that energy is neither created nor destroyed. It's just simply changing its form. Okay. When we look at energy across a chemical reaction, we're going to look at the energy of the reactants. We're going to look at the energy of the products, and we're going to see how they change. So we're going to look at some initial time reactants, some final time the products, and we're going to look at how that energy changed during the chemical reaction. Before we can dive into that, we need to understand a little bit something about energy. So energy is what we call a state function. So a state function is something that depends only on the state of the system, not how it arrived there. So we don't really care how it got from point A to point B. All we care about is what is point A, what is point B, and then what's the difference between those 2 points. We don't really care about what happened in the middle. Okay. So another example of a state function to just kind of drive this point home, an example of a state function is altitude. So when we are in Wilmington, North Carolina, where we live, Wilmington, North Carolina, the altitude here is like roughly, I think it's like, we'll call it 10 feet above sea level. So the altitude is 10 foot above sea level in Wilmington. If I were to go back to my hometown, Springfield, Illinois, the altitude in Springfield, Illinois is at like 112 feet above sea level. Okay, so Wilmington, 10 feet above sea level. In Springfield, it's 112 feet above sea level. Okay, when I'm traveling from Wilmington to Springfield, all I care about is my change in altitude, okay? So change in anything is always going to be final minus initial. So if I want to look at the change in altitude, we denote change with this kind of triangle symbol. So that triangle says change. So if I want to look at my change in altitude, I'm going to take the altitude of my final destination minus the altitude of my initial destination. So change in anything is always, always, always final minus initial. Okay. So looking at this traveling, if I want to know what my change in altitude was, I would take the altitude of my final destination, so Springfield, and we said that's 112 feet above sea level, minus the altitude of my initial, so here in Wilmington, let's say we're 10 feet above sea level. So change in altitude is final minus initial, so we've got 112 minus 10, so my change in altitude is 102 feet. Okay. So if altitude is a state function, all we care about is that change, what happens from point A to point B. So to drive this home, it doesn't matter what path I take to get to Springfield, my altitude change is going to be the same. So I could take the southern route from Wilmington through South Carolina, through Tennessee, Kentucky, and then up through the bottom. Or I could take the northern route through North Carolina, Virginia, West Virginia, Kentucky, Indiana, and over. It doesn't matter which path I take, my change in altitude is still 102 feet. It doesn't matter if I travel from Wilmington, North Carolina, all the way out to California, and then all the way back to Illinois, my change in altitude is still 102 feet. So that's a state function. All we care about is final and initial, and that will give us our change. We don't really care what happens in the middle. So energy is a state function. Okay? So anytime we're talking about the change in energy during a chemical reaction, we will always talk about the final minus the initial. So that will give us our change in energy. But a little tweak here, right? When we talk about chemical reactions, we don't say the initial was and the final was. When we talk about chemical reactions, what do we talk about? We have the reactants and we have the products. So when we're looking at change in energy during a chemical reaction, our final is actually going to be the energy of the products. And our energy initial is actually going to be the energy of the reactants. So we can change this definition slightly if we want to. And instead of saying the change in energy is final minus initial, we could say the change in energy is products minus reactants. So that would be an application to chemistry specifically. So let's look at some examples here. Okay. So let me walk you through this diagram quickly, just so you can see what's going on. Okay. So on this diagram, going from the bottom to the top, we're increasing the energy. So something that's down here at the bottom would have a very low energy. Something up here at the top would have a very high energy. So bottom to top, we've got our energy. For this particular chemical reaction, I see that my reactants are very high in energy and my products are very low in energy. So as we go from our reactants down to our products, that energy is going to fall. But what if I wanted to know exactly what the change in energy was for this chemical reaction? So if I want to determine what is the change in energy, we're going to look at the energy of our products minus the energy of our reactants. Okay? So let's put some arbitrary numbers in here. Numbers are a little bit easier to follow than theory. So let's say our low energy product, something that's down here, let's say it's 10 joules of energy. And let's say the potential energy of our reactant is high. Let's call that 150 joules. So if I want to know how the energy changed during this chemical reaction, I'm going to take the energy of my products minus the energy of my reactants. So we'll take 10 joules, which is the energy of our product, minus 150 joules, which is the energy of our reactants. So the change in energy for this chemical reaction, so RXN is just my shorthand for reaction. So the change in energy for this reaction is going to be 10 minus 150. So it's going to be a negative 140 joules. Okay. So what this is telling us is, yes, we can have a negative number for the change in energy. When the change in energy is a negative number, what that's telling us is energy is being given off or released during this chemical process. How would energy be released or given off during a chemical process? Well, it could give off light. That's one form of energy. It could give off heat. So if we put our hand next to like a fire or an open flame, we feel that heat coming off. That's an example of energy being released. So the observation for a chemical reaction like this is we might feel a little bit of heat coming off of that. Okay. Let's look at another example. So for this example, we're going to do the same thing. We've got our energy diagram here. So something that's at the bottom is low in energy, something at the top is high in energy. And again, we want to know what is the energy change for the reaction. So we're going to look at final minus initial or products minus reactants. The difference in this case is that our products are high in energy. And for this reaction, our reactants are low in energy. So let's put some numbers to this and take a look. So let's say our reactants are low down here at 5 joules. And let's say our products up here are high at 100 joules. Okay. So if I want to know what is the change in energy for this particular reaction, the change in energy is going to be the products minus the reactants. So the energy of the products in this case is 100 joules minus the energy of the reactants. So the energy of the reactants is 5 joules. So the change in energy for this reaction is going to be a positive 95 joules. Okay. So what does a positive energy change tell us? Well, positive energy change tells us that we have to put energy into the system in order for it to react. So we can look at this as kind of like climbing a ladder. So going from low energy reactants to high energy products. To climb up that ladder, we'd have to put energy into that system. We'd have to apply energy. Well, how do we apply energy to a chemical reaction? Well, we heat it up. That would be one way. So we could put it on a hot plate. We could put it over open flame. So we could heat that reaction up, and that would increase the energy. So that is just a brief introduction to energy changes. One thing I do want to point out at this point, now that we've talked about that, let's just get a little terminology under our belt for these. Okay. So for that first reaction that we looked at, we said that energy change is a negative number. So energy is being released from a chemical reaction like that. This type of reaction has a specific name, and it's called an exothermic reaction. So in an exothermic reaction, energy is exiting the system, it's being released. And we can identify that as a negative change in energy. And for the second example, where it was a positive energy change, this is entitled an endothermic reaction. So energy has to enter into the system in order for that chemical reaction to take place. So endothermic is a positive change in energy. and energies entering into that system. So that is your introduction to energy and how it applies to chemistry. I hope you guys found that helpful.